Global climate models are incredible tools for understanding the potential outcomes of future climate change that people may be exposed to. But as they are updated, so too are our projections. In this work, we use a population-weighted climate change emergence framework to assess future changes in annual average temperatures for CMIP6 era models. We focus on the mid-century period of 2040 to 2060, a time within the current planning horizon of many companies and governments. Specifically, we look at, firstly, what do CMIP6 models project for future emergence of climate change by 2050? Secondly, how do these projections compare to those from CMIP5 models? Thirdly, what accounts for any differences? And lastly, why does this matter? Compiling results from 37 models and 5 emissions scenarios, we calculate climate change in terms of signal to noise, which is the ratio of temperature change in the future to the standard deviation in a pre-industrial control simulation. That is, how far will annual average temperatures deviate from normal background variability? We find that the tropics, near the equator, exhibit climate change emerging soonest and most strongly, due in large part to their lower interannual variability in annual temperatures. We combine these results with gridded population projections to calculate exposure. By 2050, most models agree that even under a moderate emissions scenario, around half of the global population will be exposed to so-called unknown temperatures, here meaning a signal-to-noise ratio over 3, and over 90% will be exposed to unfamiliar temperatures, signal-to-noise over 2. There's significant inequity in this exposure. For example, people in ASEAN countries will be exposed to much more abnormal temperatures than those in OECD countries, despite the latter tending to be the highest emitters per capita. There are some significant changes in these projections compared to the earlier CMIP5 generation of models. Signal-to-noise is generally higher in the CMIP6 ensemble, due partly to higher model sensitivity, as well as to changes in the specified emissions pathways. There are, however, some areas where climate change emergence is lower, most notably in Central Africa and South Asia. These regional changes arise in large part due to the changes in aerosol loading between model generations, as well as changes to the effective radiative forcing of models to individual agents, and how features like the AMOC ocean current respond. These regional changes mean that temperatures in some areas may not go as high as previous models suggested. These findings also show that pattern scaling approaches may be out of date and inaccurate if based on CMIP5 era results. The inequity of exposure to climate change that we show in this work bolsters the argument for global cooperation and underscores the importance of investing concurrently in both mitigation and adaptation.